Hello, welcome everybody to the Climate Dynamics special session for the Climatic Research Unit's 50th anniversary. So welcome to all of you here. So I guess CRU is perhaps better known for climate data sets, but actually since CRU started we've worked on the dynamical processes that govern regional and global climates and hydrological cycle and so on. So it's not new for us. In fact, for our 50th anniversary, I was looking through the PhDs, 74 PhDs completed within CRU in the last 50 years, and at least half of them fit within the broad field of climate dynamics. Having said that, this aspect of CRU's work has really expanded in the last decade or so as the main focus of many of CRU's staff and students now, including our speakers today. So we have arranged 4 short research meetings to celebrate CRU's 50th year. We've already had one on paleoclimate and one on the instrumental climate data and its use in attributing causes of climate change. And now we're on to the 3rd one, which is on climate dynamics. And when we heard that UEA were hosting the National Climate Dynamics Workshop, it made sense to combine the 2. So Manoj, Dave, and Ben have kindly agreed to let us have a CRU50 session within this bigger workshop. And we moved up here so that we can have it as a hybrid meeting. So we have a number of people online as well who are joining especially for this session. So thanks for all coming. And we will therefore have a mixture of questions from in the room and from our online attendees when we get to questions. Okay, so we're going to move straight into the first talk. So Dave Thompson, who has a joint UEA and Colorado State position, and he came over to UEA last August, and he's going to talk about the changes in surface temperature persistence when the climate changes. Thank you.
Thanks. Yeah, this room's good for social distancing. Right, okay. I'm Dave Thompson. I didn't put the prof thing on this slide. I just want to say that. Dave. Okay. Anyway, this is work done. This is work done by myself with 2 graduate students. One is Jingwan Li, who's at Colorado State, and another student is Shim Yuk. So the work with Jingwan Li was published this last year, and the work with Shim Yuk is in that sort of weird stage where it should have been, you kind of like feel guilty every day when you wake up because you haven't written it up yet. So half the work has been written up, 40% should have been written up, and 10% is just like, makes no sense. I don't know where we're going with it. Okay, so the context for the work is obviously there's extensive work done on changes in the mean climate under climate change, right? So we have decades and decades of work on this, and we understand how the mean temperature is going to change for the most part. We have some ideas about how mean precipitation will change, etc. There's less work, but quite a bit done on, say, changes in not the mean, but in the variance and the skewness of different aspects of climate. So, for example, there's the work by James Screen and Tapir Schneider, for example, on changes in temperature variance, right, which are expected where you've changed the horizontal structure of temperature, where it changes, and then temperature advection across that will give you changes in temperature variance. There's a fair bit of work on the skewness of climate, the nice stuff by Talia Taman-Brodsky, for example, in the last couple of years, on how skewness will change. And I'm mentioning the studies where you can sort of sit down with pen and paper and come up with a reason why these should change. It's not just looking for it. And so what I'm going to highlight today is some stuff that we've been doing on changes in the persistence or in the memory of climate. And I'm focusing on daily time scales and how does that, has that changed? Well, actually not has it changed, it's will it change? So there's a bit of work done on observations on this, but if you were to go and look at observations and try to detect changes in persistence, but my personal view is that you kind of convince yourself of anything, really. It's right on the fringe of significance. But in the models, the story is different. So maybe there's something that is embedded in the noise. So the talk will have, what I'll do first, 20 minutes, is I'll first show results from some Earth system models. So it'll be 150 simulations, and I'll just show you this is what the Earth system models show in terms of changes in persistence. Then I'll show some results from simpler models. So it'll be a different hierarchy of relatively simple models and how persistence changes under climate change. This is all under climate change in those. Then I'll speculate on why these changes might have occurred, and then where we're going with it. And that's kind of where we'll go. So for the Earth system models, we're looking at 150 simulations. We have daily output from four large ensembles. So each large ensemble, I guess everybody here knows this, right? You have the same forcing, you have different initial conditions, and you project into the future how climate will change in this case. So the work actually started with the NCAR CESM. There's 40 simulations on that. And then you can see where the models are up there, the Australian, Canadian, and GFDL. There are other large ensembles that we haven't poked. It's so much output, right, that we just sort of started with this, and maybe we'll move on. In fact, it all started with the NCAR model, and the story was really nice and simple with that Earth system model. You had this nice paper, and then you're like, oh, we should check another model, and then you check it, and the story falls apart, and that's how the world works, but I'll show you that. And I'll advertise, if you're not aware of it, but the NCAR, Adam Phillips and Clara Dessa have made this output so accessible. So if you're a student, for example, right now, it's hard to work with some of this output, but they've made it very, very accessible, and you can get climate indices. Anyway, Adam's great. So the way we did it in these runs is you remove the ensemble mean first. So these are climate change runs over 100 and something years, temperatures increasing, and we're looking at how the memory of climate changes. And of course, if you don't remove the force signal, you're going to get changes in memory just because the warming is accelerating. So you remove the ensemble mean from each of these Earth system models, from each large ensemble, and then we calculated first of all, I'll show you the daily resolved lag autocorrelation at all grid points. So you take there's different ways of doing persistence. You could find some threshold and count the number of days, but one very simple way of doing it doesn't really matter. It's just to calculate the daily lag autocorrelation. So you take the daily lag autocorrelation as a way of quantifying persistence. It's all daily mean temperature. And then you calculate that at each grid point. And then you could use different lags for this. We just use lag 10, for example. It doesn't matter qualitatively what you use. So we're just going to look at what is the lag 10-day autocorrelation of temperature between 1970 and 2000, and what is it between 2070 and 2100. So a 100-year period differed by, again, you have some rate of forcing in there, right, due to the prescribed increases in greenhouse gases and the water vapor changes. Okay, so I'm just going to compare these two periods. We're going to look at the lag 10-day autocorrelation in this period and in this period. And then this is an example of what this looks like. So this is not from a model. This is just from me and MATLAB. And so the solid line is the autocorrelation of a red noise time series with an e-folding time scale of around 10 days, just so you get a sense of what that looks like. And then the dashed line would be if you had a 50% increase in the variance explained by the lag 10 days. So if R squared would be the variance explained, and if you had a 50% increase, that's how the lag autocorrelation. So for example, if this was Norwich temperatures, for example, in one period, and the map I show you has a 50% change, that's what the correlation, the memory of how the memory of temperature here has changed, if that was the case. So that's just what it looks like in terms of a 50% increase. So here's the results. This is averaged over 150 all 150 simulations. Wherever it's red, the memory in surface temperature has increased in these simulations, and where it's blue, it's decreased. Again, this is averaged over 4 different Earth system models, and that matters. And again, 50% in this plot, wherever you see 50%, that's kind of like what the previous figure showed. It's a pretty substantial change. And wherever there's a dot, the difference is significant, and it's really significant. Just because you have 3,650 days in this record and in this record, and then you have all those grid points, and then you have 150 simulations. So there's a lot of statistical teeth in that. Right, so again, when we first did, if you just look at NCAR, the NCAR CESM, the whole world is red. And the story is nice and it's simple and everything is increasing everywhere. Who knows why? Then when we look at, if you look at GFDL, if you were to start working with that instead, you would have pretty much everywhere is red, except for the tropics would be blue. And a little band in the Southern Ocean would be blue too. And then the other two models would show red pretty much everywhere. So the murkiness of the results in the tropics is largely coming from the GFDL model. And then it's pretty much red everywhere else. So it turns out what matters, I feel like I'm just really projecting in here. Good. So what matters in the tropics for persistence is ENSO. And so if your model has an increase in ENSO amplitude, then you get more power on the seasonal time scale, and you just simply have more memory because of that. So the NCAR model and the other two have increases in ENSO power under climate change, and the GFDL model has the opposite from that. And so that's why you see those differences in the tropics. So if you want to understand how the memory, and the memory matters, right? Because this is, if a heat wave lasts 5 days versus 8, this matters. If you want to understand how persistence changes in the tropics, and then you have to consider how your model handles ENSO. And there's good reasons to think, even though it's an outlier, that the GFDL model is getting it right. But that's a different topic for another day. The most robust changes are in the Arctic over the surface, and you can kind of, I'll come back to mechanisms, but you can imagine why that's the case. It's because you had a bunch of sea ice from 1970 to 2000, and suddenly you don't have it. In the latter part of the 21st century, you remove the sea ice, you increase the surface heat capacity, and that gives you much more persistence in that region. The blue in the Southern Ocean, it turns out that's mainly coming from GFDL. So across the globe, the projections under climate change are that the mixed layer of the ocean will become more shallow, or at least your stratification will increase in the surface ocean, and that would decrease the effective heat capacity of the ocean surface, and so that should decrease persistence. And in the GFDL model, they have some really robust mixing, especially in the Southern Ocean, so you have a really deep mixed layer, and that shows much more than it does in any other model, and hence that sort of blue band there. So that's the nice thing about different models showing you different things, is that it gives you clues to try to figure out what's happening and why this is happening. But in general, the biggest changes in general, it's increasing over most of the globe, but it's not increasing by a little bit, right? This is a 50% increase in variance explained. That's a pretty substantial change in how you would perceive weather if this was to happen. And so the question we're really sort of playing with is, with the exception of, say, ENSO and regions where it makes sense, like sea ice melting, why are most of the oceans, particularly across the northern hemisphere exotropics, why is the memory increasing, the surface temperature? So the next set of results I'll show you is, and then this is a slide, but it just says what I said. For the most part, you get these increases in persistence with the exception of the tropics, and this is mainly coming from the GFDL model. I should mention that I don't put too much stock in little blobs in these plots, right? You'd want to look at the seasonal discretization, which I'm not going to do here, and also the model-by-model discretization. But that little blob in the northwest of North America is pretty much there in everything you look at, for example. But some blobs aren't, and those ones I would ignore, personally. Okay, so then I'll show you some output from some idealized runs, and then I'll go into mechanisms more, and then talk about what we're doing with it. So in the idealized, this is output. The paper is Jihong Tan's paper with Tiffany Shaw, and I'm kind of like a parasite. I like borrow other people's model experience. There's so much output out there. It's already being done, right? And I don't know how to run these models myself. So anyway, that's not really true. But this is output from simulations that they did. And there's 3 different climate change simulations I'm going to show. There's 2 from GFDL, from Jihong Tan, and 1 out of Max Planck that was with Thorsten Martz and Bjorn Stevens. And so in the first 2 simulations, there's a control simulation with something like current CO2, and there's a 4 times CO2 simulation. These runs have a slab ocean of about 30 meters, I think it is, and that doesn't change. So there's no way for the ocean heat capacity to change. There's no sea ice, and there's no land-sea contrast, but they have full atmospheric dynamics and et cetera, et cetera. So you're just stripping out sea ice, and you're stripping out changes in the surface heat capacity from these runs. The top one has gray radiation. This is like Dargan Frierson's model, where you prescribe the emissivity. So you just say, this is what the emissivity is going to be, and you increase it in a way that you get the right surface temperature change to match a 4 times CO2 run. The other one has comprehensive radiation, RRTM, and so you, again, just increase CO2 by a factor of 4. And then the last simulation, it's also an aquaplanet slab ocean. This has comprehensive radiation, but this is a tropic world simulation. So F is 0 everywhere, and the insolation is homogeneous. So there's just 3 different frameworks to see what happens. So what I'm going to show you here in the first plot, this is the output from the fixed emissivity. So you take the emissivity, the long wave emissivity of the atmosphere, and increase it. And it's shown for the exotropics and then for the tropics. And the black line is you take the autocorrelation at each grid point and average it then over every grid point. So it's not the memory of the hemispheric mean temperature, but it's the hemispheric mean of grid point temperature, right? And that's what the black line shows. And the gray line is when you just increase the emissivity, then you get a difference that's not that different from the previous plots, 50%-ish or something in terms of an increase in memory. The tropics, you also see that. So there's some evidence that even in these simple frameworks, you're getting increases in persistence. This is one of my favorite plots. This is the exact same model as if you took some aquaplanet GCM, you had comprehensive radiation, and you increase CO2 by a factor of 4, and this is a different universe, right? If this was to actually happen in the world, then you'd know it, right? So what's nice about this, though, is that we should be able to tease out of these models what's going on and why that's happening. But if this is what's humming underneath the Earth system models, and this is the same radiation scheme and the same basic dynamics in the Earth system models, and there's something big in there. And this is the tropic world simulation, and now the x-axis is showing month here because that's the only output we had, but the point is with a very different setup without, say, a jet or any blocking or anything like that, because it's all the tropics, you still get a very large increase in memory there. So I guess I got a few minutes left. So this is one framework that we sort of started with to understand why this would change. And just one way you can think about it is if you had a simple this linearization of the first law of thermodynamics, you can kind of do some back-Lindbergh calculations to see why persistence should change. So if you change the effective heat capacity, as I've already mentioned, you're going to change the persistence of surface temperature. If you change F, you can think, yes, you'll change the persistence of surface temperature. And so, for example, ENSO would be, say, the dynamics from that. And then, say, jet dynamics could do that. But again, there's no change in C in the slab ocean models, and there's no change in F in the sense that there's no jet dynamics, at least, in the tropic world simulation. There's no ENSO in any of those models, so that can't be it. So my favorite explanation is that there's something in the damping of surface temperature anomalies that's humming underneath all of this. And what that change in damping is, I'm not sure, but I haven't quantified this. This is where it gets into that 10% of the work where I want to do this, and we haven't done it yet. As you could imagine that as the long wave opacity of the atmosphere increases, that the radiative damping timescales might increase, and that might be humming underneath no matter what else is happening, sea ice loss, et cetera, you've always got this thermodynamic and radiative constraint humming underneath where the damping of temperature anomalies increases simply because the long wave opacity of the atmosphere has increased. It's also possible that, I haven't checked this and it might not be the case, but whether the latent heat flux feedback at the surface, whether that has changed in any way, because that should scale with Clausius-Clapeyron, if that plays a role. But the last slide I'll show, the last science slide, is just one other framework that kind of gets at why the damping might be important. So this is these are the experiments that we're doing, but this is not the experiment we're doing. So this is from a paper by Tim Cronin, came out a while ago, and it's just looking at the time scale of relaxation, a radioconvective equilibrium, coupled to a slab ocean at the bottom. So this is just a column in radioconvective equilibrium, coupled to a slab ocean. And the x-axis down here, I always get those confused, x-axis, along the bottom, you can imagine they're varying the mixed layer depth. So just take the dashed line, that's a mixed layer depth of, say, 18 meters, for example. And then the y-axis is the surface temperature that the model's equilibrating to, and then the colors are the time scale in days of the restoration to rate of convective equilibrium after you whack that climate system. So the point is, even a very simple column RCE model coupled to a slab ocean, the timescale goes up substantially, right, as you increase the temperature. So the physics of what's going on is presumably embedded even in that simple case, and that's why we're toying with radiation. So I think that's all I got. Time. It always feels weird in a short talk to even have conclusion slides, right? But the main take-home message is okay, so persistence is important for surface weather. And this is only surface temperature I'm looking at, and models basically, all the model simulations suggest it's almost assured of changing, and a variety of processes seem to be important, at least in the Earth system models. But I don't know which key processes are key here and which are key there. And it's, it's analogous to work on, say, trends in blocking, but that's really hard to pin down that, right? And this is trying to get at something more general. And is there a fundamental radiative constraint is where we're headed with it. And that's all I got. So.
Great, thank you. Any questions for Dave? In the room first.
Oh, yeah, I forgot this.
I think there's one. You were first, I think. And if you can use the mic, if you're in the room, so those online can hear us.
Thanks for a really interesting talk. I was just wondering about the historical part of those large ensembles ones. Has there been any change in persistence over the 20th century? So, for example, maybe due to aerosol forcing in the sort of 60s, 70s, or is there any sort of like structure in the 20th century persistence in those ones?
Yeah, it's...
Decadal
I can't remember, to be honest. So we started off investigating with a larger forcing over this 100-year period, and we looked at the observations, and there are papers on the observations, and then it's really, I don't think there's really any observational support for it, and so we just set aside looking at the 20th century in these models. But yeah, I should. Xinguang graduated. It was kind of tricky to...
I think Adrian here had a question, and maybe there's a hand up further back as well. Not sure.
Do you see an increase in mixed layer depth over the oceans in those system models to help explain the persistence there?
It decreases. The mixed layer depth decreases over the ocean, at least the effective surface, because of the stratification increasing. So the mixing becomes less vigorous in general. So, and there's a paper that came out by Rob Wills in the last few months, actually, that really, it's been around for about a decade, that notion, like Mike Alexander and others have done work, and then Rob Wills has a paper just in the last few months, and its title is something like Reduced Persistence Over the Oceans Due to a Shallower Mixed Layer, or something. So it would be the opposite of this.
Michael, do we have any questions online at all?
No, we've got 18 people online.
Okay. Yeah.
Maybe I'm, maybe I missed it. Have you looked at this in just dry simulations, like Health Suarez or something like that? Do you still see, or does this need moisture?
Yeah, I didn't know how to do radiation in that. We thought about it. I wasn't really sure, because it's, well, you could change the relaxation time scale to the rate of equilibrium, but then it's like you're telling it what to do, kind of.
Oh, I see what you mean.
We wanted it coupled to a surface. We kind of thought about it, but we didn't do it.
Yeah, I guess it depends what the, yeah, I know.
But you could change the damping time scale that you use, to the rate of equilibrium profile, but then it felt like we were building it in a little bit.
I was thinking just warming the whole planet up and seeing, I don't know, seeing what autocorrelation does. In simulations where I just warm the pole up, I see longer time scales of temperature.
You could just increase everything, the temperature. We haven't
and
done
then
that.
if you left the, I don't know. But yeah, you're right, kind of the physics is a bit, prescribed, so.
We haven't done it. It could be great. I don't know. I haven't done it. So.
I think the last question from Pete, is it? I can't see. Yep.
Thanks. I was just wondering, can you say in any kind of quantitative terms how much of an effect this could have on heat waves on land, like just in terms of like length, number of days above a heat wave threshold, or magnitude of heat wave or whatever?
No, I mean, these are great questions. It makes me feel like I should have like multiple students that could play with this. But yeah, like I started off with those two curves. Like what is it? I'm lying. We actually did do that in the paper. Now I remember. It's in the supplementary material where you have on one axis the length of a heat wave, and the other axis the change in the quantity I was showing there in the map, and of course they scale with each other. And yeah, we did do that. I just don't remember it offhand. So.
Okay, thank you. I think we should thank all three of our speakers from this excellent session. So thank you for joining us. Thank you for joining us online as well.